Okay. Thank you very much. Good morning, everybody. We're done with the technical difficulties. Let me greet you. And first of all, I want to say thank you for the invitation. It's a great pleasure to be giving this talk here. So I'll be talking about insights from radio surveys about AGN feedback, really, black hole mass growth across cosmic time. And much of the results, better to say, will be based on the VLA-COSMOS survey. So I definitely, you cannot see my pointer here, right? Oh, you can see my pointer here. So many thanks has to go to the collaborations and to the students and postdocs and collaborators who have contributed this work, both from the VLA-COSMOS survey and also from the XXL surveys that I will talk about later. So let me first successfully change the slide. Okay, the meeting is being recorded. Come on. So this is the outline of the talk, essentially. So I'll give a broad introduction about radio AGN and their role in galaxy formation and evolution. Then I will talk about the VLA 3 GHz Large Project, which is our largest radio project in the Cosmos survey. Then I'll talk about the challenge of classifying galaxy populations in radio surveys, such as the VLA-COSMOS survey. And then I'll conclude with our results on the cosmic evolution of radio AGN and the implications of this onto radio mode feedback since redshift of 5. Oh, it's working. So let me start off with the broad introduction. So in general, we all know that we live in a world where we mainly have blue and red galaxies. And in our standard picture of galaxy evolution, we see, at least in the local universe, that there is a blue cloud and a red sequence with the intermediate region called the green valley. And galaxies in our standard picture today evolve somehow from the blue cloud to the red sequence. And we see that the distinction of these two galaxies is, these two types of galaxies is basically manifold. So the blue galaxies are mostly disk galaxies. They have abundant star formation and gas inside of them, while the red sequence are early type galaxies, spheroidals with no or little star formation and gas. So in our standard picture, blue galaxies evolve into red galaxies, and we are still trying to understand how exactly this process is happening. So definitely by a conversion of gas reservoirs into stars, mergers of galaxies are important, at least at a high mass, and passive fading of stars is also important. But one of the ingredients in our models of evolution is also AGN feedback that I will focus on in this talk. So nowadays, cosmological models, semi-analytical models, very regularly invoke AGN feedback in the process of galaxy evolution. But the real question is there really an impact of AGN on galaxy evolution? And if there is, how big is the impact? So that's kind of the major question that I'm trying to follow up and find the answer to in my research. So to explain the AGN feedback in cosmological models, in short, usually there's two types of feedback that are involved, and they have different names in the literature. Quasar mode is one of them, and radio mode is the other one. So the quasar mode is more or less a truncation mode. It's merger driven, and it's associated with vigorous black hole mass growth, vigorous accretion. And the basic idea behind it is that quasar winds expel a fraction of the galaxy's gas, and thereby they terminate the quasar and starburst phase of the galaxy. And this is not necessarily linked to any radio emission. Now, the second type of radio mode is also called maintenance mode very often in the literature. And this one is assumed to be related, as the name says, to radio emission that you would observe from a galaxy. And it's assumed that once a hot static halo around a massive galaxy forms, which is associated with modest black hole growth, radio outflows in the sense of radio jets and lobes occur, and they heat the surrounding gas to the limit where they then limit the collapse of the gas to form new stars. And in this way, the radio mode feedback in cosmological models accounts for the truncation of further stellar mass growth. And it is directly related to the radio outflows of galaxies. And the combination of these two types of feedbacks in models gives a good reproduction of the galaxy properties. So here are two examples from two cosmological simulations that I'll be using throughout the talk. So one of them is taken from Croton et al. 2006, and the most recent version from 2016 or 17, I think, is called SAGE. And in the right plot, I'm showing the GAL form, Bauer et al. 2006, with more recent improvements of the model. So what we're looking at basically is the luminosity function in K-band in both plots, which is essentially proportional to the stellar mass of a galaxy. So we're looking at the stellar mass function. The dots in both points are taken from observations. So these are observational results, and the curves are the reproduction of the model of the stellar mass function. So as you see, for example, in this model, if no AGN heating is involved, what the models produce is too many massive galaxies. The same occurs here in the GAL form model. This is the dashed red curve shown here. And once they switch on the AGN feedback mode, in particular the radio feedback mode, they are able to reproduce the high mass end of the stellar mass function. The question, however, is, of course, is this really happening in such an important statistical sense in the real observed universe? So to go on from the models, and this is now another plot taken from the SAGE model, where now here the supermassive black hole accretion rate density is shown as a function of redshift in the simulation. So again, two curves, one for the quasar mode and one for the radio mode. Now, in the SAGE model, the assumptions are that essentially the gas, the hot gas, is accreting onto the supermassive black hole via Bondi-Hoyle accretion. And the luminosity, which is assumed to be 10% of the m dot c square, is taken as the source of heating that offsets the energy losses of the cooling gas, which truncates then the further growth of stellar mass in galaxies. Now, this in principle can be inferred from observations. The same curve essentially can be inferred from observations. However, there's some challenges to be tackled to be able to get the data set, a statistically large data set that will allow you to derive such a curve in this plot to compare to the models in the end. So first of all, what you need are deep observations. So you can reach high redshift sources, but you also need observations over a large enough area on the sky to have a statistically large sample, to have enough galaxies so that you can divide them into many bins out to the high redshift, and still in every bin have a statistically significant number of sources. Of course, for this, you need precise redshifts. And you also need a good AGN classifier because you don't want to contaminate your sample. And then once you have such a survey with all these parameters calculated, you can go further and calculate the radio mode luminosity density, essentially from the observed radioluminosity using some scaling relations and compare it to the semi-analytic models. So this is essentially kind of the recipe that I'll be using in this talk later to show you when I show you the results, they're based on these steps. So let's start off now with what we actually know about radio AGNs from studies of, let's say, lower redshifts lower than 1. So first of all, when we observe in the radio, here I'm referring to mostly 1.4 gigahertz frequencies. So these are megahertz or gigahertz frequencies. And the most common ones are listed here. So nowadays, I think the most common one is 1.4 gigahertz. 3 gigahertz is also used recently with the VLA being upgraded, and the earlier surveys have been a lot taken at 150 megahertz. So what we observe is basically synchrotron emission from the galaxies, and synchrotron emission from faraway galaxies arise from 2 physical processes. One of them is star formation, and the synchrotron emission basically is an outcome of the supernovae explosions and the acceleration of the particles due to the shock waves of the supernovae. And from the second source of the synchrotron emission is from active galactic nuclei, from the cores, the jets, and the lobes. And here there is a nice example of one of the resolved galaxies with large radio jets finishing off with lobes. So this is the synchrotron emission from the jets, which are accelerated most likely in the vicinity of the black hole. Now, in terms of radio AGN, when you look through the literature, it can really get confusing in terms of the various classifications. So this slide here is to summarize the various classifications. First of all, one of the commonly used classification is the Fenner-Riley type 1 and type 2 sources. And this classification is based on radio galaxies that you can nicely resolve. 2 examples are shown here. So if you have such good observations that you can really resolve your sources, Fenner-Riley found that sources can be distinguished in such a way that some have more than half of their total luminosity associated within the inner half of the source. These are called then FR1 sources. And if the bulk of the emission is in the outer part of the source, these are the FR2 sources. Now, based on the radio spectrum, if you have multiple frequencies and you can look at the spectrum, there's also various definitions, distinctions between AGN. So in literature, you find steep sources versus flat sources, gigahertz peaked sources, etc. Radio loudness is one of the most common ways to make a distinction between radio sources into radio loud and radio quiet. However, this by itself also gets to be very confusing in literature because there's various definitions and sometimes they are opposing the other. So in some definitions, radio loud sources are those that would be radio quiet in another definition. And this is because the distinction, one way to make the distinction is to use just radioluminosity. And the other way is to use a ratio between radio and some other luminosity. And then to define a threshold above and below which you'll call something radio loud and radio quiet. And optical spectroscopy is also very commonly used. We're not looking essentially at the radio sources, just requiring that the optical source has a radio detection. You can use optical spectroscopy to divide your sources based on the optical spectroscopic line ratios into low and high excitation radio AGN. So if you have observations that are nicely resolved, you can use classifications on the top if you have the radio spectrum as well. But in deep surface, you often have an most often you have an unresolved radio source with one flux point, one luminosity point. So it really gets to be difficult how to classify your AGN. So we have to go to classifications that are here listed in the bottom. So optical spectroscopy has been used to classify many radio sources, for example, in the NVSS, SDSS survey, etc. And this is based on the BPT diagrams shown here. So essentially, these are diagnostic diagrams that separate star-forming galaxies based on emission line ratios from high excitation and low excitation galaxies. So if one assumes that there is a correlation between the emission that you find in the optical diagnostic diagrams and the source of radio emission, essentially you can use the optical emission lines to select Seyfert galaxies and QSOs, which would be type 1 and type 2, by selecting high excitation radio AGN from the optical diagnostic plots. And you can select low excitation radio AGN by selecting liners from the diagnostic plots and taking simply absorption line galaxies that do not have any emission lines from their spectrum and putting them in the low excitation radio AGN category. So let's look at the results on the properties of radio AGN when this classification scheme is applied to a sample of SDSS and VSS lower redshift sources. So it's a spectroscopic sample where you can nicely, based on optical spectroscopy, make a distinction between the high and low excitation radio AGN. So if one looks at the color, G minus R here, the low excitation radio AGN occupy this part, while the high excitation radio AGN occupy this part. So statistically looking, the average color of the low and high excitation radio AGNs are different. The low excitation radio AGNs appear to be statistically looking redder than the high excitation radio AGN. But note, there is an overlap. Now, one can go further and look at their stellar masses. And again, statistically looking, the averages are on different parts of this diagram. So high excitation radio AGNs appear to have lower masses on average than low excitation radio AGNs. If one looks at a proxy for the black hole mass, it turns out that the low excitation radio AGNs on average have higher black hole masses than the high excitation radio AGNs. And if one looks at the accretion rate in units of Eddington accretion, it's the other way around. Low excitation radio AGN tend to have a lower accretion rate than the high excitation radio AGN. So there really seem to be some statistical differences between the two types of AGN. To put this further, in 2006, I think, Evans looked at the X-ray properties of radio AGN from the 3CRR sample. And they concluded that, so in their sample, the high excitation radio AGNs, they concluded that their nuclear X-ray emission is dominated by heavily absorbed components, and that this is consistent with the origin in a putative torus around the black hole. And they conclude that it is a radiatively efficient flow that is surrounded by a putative torus in those AGN. For the low excitation radio AGN in their sample, they have shown that the nuclear emission is unabsorbed and that the correlation between the X-ray and radio emission suggests that the origin of the X-ray emission are the jets of the sources. And they conclude that any accretion flow related component is likely to be highly sub-Eddington and must have low radiative efficiencies. So one can then say also about the sources that high excitation radio AGN are essentially, looking on average, radiatively efficient accretors, while the low excitation radio AGN are radiatively inefficient accretors. Now, Ellen et al. Have put the studies of this topic further by looking at radio galaxies with jets in X-ray clusters with cavities that the jets are inflating. So from the jet powers, so they calculated the jet powers from the inflated cavities from the X-ray emission, and they calculated the Bondi accretion rates from the gas density profiles and from the black hole that they inferred from the velocity dispersion. And what they found is that there is a correlation between the jet power on the x-axis and the Bondi accretion rate power. So from this, they conclude that spherical Bondi accretion could provide a reasonable description of accretion on the supermassive black hole in elliptical. So those are low excitation radio AGN in the terminology from before. And furthermore, the idea has been put forward that low excitation AGN could be accreting the gas from the hot phase of the gas, and high excitation radio AGN could be accreting from the cold phase of the gas. But more recent results indicate that this is not as simple, that there's also low excitation radio AGN that are accreting from the cold phase of the gas. And to look at this from a more theoretical perspective, this all seems to be consistent with thin disk models versus advection-dominated accretion flows. So from a theoretical perspective, when the accretion rate drops to below about 1 to 10% of the Eddington accretion rate, the accreting mechanism basically changes, and the thin disk at a low accretion rate, the geometrically thin, optically thick disk essentially becomes geometrically thick, but optically thin disk, which is illustrated here, which then fuels the black hole and also makes it more favorable for radio jets to emerge from such a structure. So in essence, what we're learning from the studies of AGN is that there's basically two main types of AGN in the universe with lower redshift of 1, named differently in the literature. So on one side, there's the standard AGN, which are called high excitation AGN or thin disk AGN or radiatively efficient accretion flows. So they would be selected by X-ray emission, by all of the standard AGN selectors, X-ray emission, mid-infrared, optical, spectroscopic lines, and they would fit into the unified model of AGN. And on the other hand, we have AGN that are selected basically purely in the radio regime, for example, by seeing large jets coming out from the galaxy. So their optical spectrum is devoid of strong emission lines, and those are called in literature with various names: low excitation, thick disk, radiatively inefficient accretion flow. And just to summarize this a little bit differently, so the two types of objects, the standard, the unified model AGN and the thick disk AGN, show different properties, statistically looking different properties in such a way that low excitation AGN are the ones that have a lower radial luminosity, are redder in optical colors consistent with the red sequence, have a higher stellar mass, have a higher black hole mass, have a lower gas mass, and have lower accretion rates. However, remember when I said that the classification based on optical spectroscopic diagnostic tools essentially assumes that the radio emission is correlated with the findings of the optical emission line properties. So in a sense, if if based on the optical emission lines, you select an AGN, whatever type, you assume that the radio emission is also of that source, which is not necessarily true. And indeed, when one looks at the color magnitude diagram, where you see that low excitation radio AGN very nicely populate the red sequence, and the high excitation radio AGN are here closer to the blue cloud in the green valley, and you actually look at how the star formation increases in this diagram, that would be roughly followed by this blue line. So one needs to be very careful in making this assumption that the optical classification actually relates to the radio, to the source of the radio emission that we observe. So we looked at the star formation properties. Then again, in a sample of NVSS, RS, and SDSS sources, again at low redshift. And the sources, the radio sources, have been selected based on the optical spectroscopic lines. And we looked at the star formation within the sources by deriving the star formation via SED fitting. And in these diagrams, the radial luminosity at 1.4 gigahertz is shown as a function of star formation rate. And the line in every point and the grayscale in the background are the star forming galaxies, which should be following a correlation between the star formation rate and the 1.4 gigahertz luminosity. As we know that one of the sources of the synchrotron emission we observe is the star formation rate. Yet again, if you have radio AGN in this plot, of course, you will see AGN offset from the correlation that you expect for star-forming galaxies. And based on this, we could statistically compute how much of the radio emission within a certain category, optically selected, arises from star formation or from AGN activity. So for high excitation radio AGN, we find in this particular sample that about half of the radio emission arises from star formation processes, half from radio AGN. Yet for low excitation radio AGN, mostly the radio emission is due to AGN emission. And this is consistent with newer results on the topic. So let me summarize this lengthy introduction into radio AGN. So radio AGN are deemed to be the drivers of the AGN feedback in cosmological models. And we find two fundamental types of radio AGN: radiatively efficient AGN, which are called often high excitation radio AGN, which have lower black hole masses, and they accrete at roughly Eddington rates. And we have radiatively inefficient AGN, which often are called low excitation radio AGN. In literature, they have the largest black holes, supermassive black holes, and they accrete at significantly sub-Eddington rates. All types of AGN can be detected in the radio, given, of course, if you have high enough sensitivity. But the source of radio emission may arise from AGN activity, but also from star formation activity in the galaxy, which one needs to be careful about. Let me now switch to the 3 GHz Large Project that we have conducted towards the cosmos field with the Very Large Array. So the cosmos field, it is a 2 square degree field in the sky, which has been in the last decades observed through all of the wavelengths available essentially, and most of the ground and space-based telescopes. And within that survey, once the Very Large Array was upgraded and yielded much better performance than it did previously, we conducted a close to 400-hour observation program towards the cosmos field at 3 gigahertz at a resolution of 0.75 arc seconds. And we managed to reach a depth of about 2 microjanskys per beam, which makes the survey simultaneous with the largest and deepest radio continuum survey at such a high angular resolution. And the benefits of this are, of course, that you sample the faintest objects, which are the highest redshift AGN and star-forming galaxies in a statistically significant way, so that you can construct the statistical samples that you need to construct luminosity functions, luminosity density functions, radio mode functions. And in the field, we select close to 11,000 sources down to 5 sigma. So the observations were taken over, I think, 2 years, mostly under good conditions. And the calibration and imaging of the data was a little bit challenging because that was the first such project with the upgraded VLA. CASA wasn't developed enough to do all of the tasks needed, and the APES was not applicable anymore to the new data set. So we had some challenges, but we managed to reduce the data, image the data, and test the data in various ways. So this is the map. It's more than a few years of work. And this is what the 2.6 degree map looks like. It looks like a black box, essentially. And I find this very funny in radio surveys. No matter how much time you devote to a project, your map looks like this in the end. But to zoom in, we have some very nice radio galaxies. This one is one of my favorites with bent jets. If you look at another part of the field, again, large radio galaxies, but here we start to see the point sources, which are the typical sources in the field, and the reason why we actually wanted to observe cosmos in radio to such depth. And this is a very typical part of the field where we mostly have point sources. So one flux measurement for our radio source, and these are the faintest, highest redshift objects that we are actually interested in the most. So we tested the data in many various ways. We extracted the catalog of sources using Blobcat, particularly looking at sources that could be multi-component sources. So many team members separately looked at the sources to put multi-component sources together. And in the end, we published a catalog of close to 11,000 sources, which is publicly available. And we've done a lot of tests to assess the quality of the data, the completeness of the data, the astrometry of the data. And just to summarize where the VLA-COSMOS survey is in context of earlier surveys and surveys that are under construction and currently being performed, it kind of bridges the past results to SKA and results that are coming out. In terms of luminosity versus redshift, if you look at the NVSS first surveys, the results I have shown in the past slides, so they would lie somewhere here. And the VLA-COSMOS 3 GHz survey, so the flux limit of the survey is the line shown here. So in terms of AGN, you could use 10 to the 25 watts per hertz as a sense of one definition of the radio loudness to select high power from low power radio AGN. And as you see in the 3 GHz survey, you can actually get very good, almost complete samples of low luminosity, low power radio AGN out to high redshifts, which is relevant for this talk. So to summarize, we have close to 11,000 sources in the VLA-COSMOS 3 GHz survey down to 5 sigma. The RMS is 2.3 microjanskys per beam, and the resolution 0.75 arc seconds. Now, let's go to the next challenge we had to tackle, and this is how to select the galaxy populations. So, as a summary, optical spectroscopic diagnostic tools are the tool used in the local universe very much to distinguish radio sources, and it is an excellent method. Yet for deep surveys like the COSMOS survey, where you go down to magnitudes in the optical to 26, 28 or so, it is really impossible to get a high quality spectrum of every single source, and the sources are redshifted, so the relevant lines used in the local universe are out of your standard optical spectrum. So one relies on proxies to distinguish AGN from star-forming galaxies, and there's many approaches to this. You can use X-ray or infrared selection criteria to select AGN. You can compute rest frame optical colors to select blue from red galaxies, which correlates with the optical diagnostic diagrams, or you can rely on the infrared radio correlation, which is in essence the correlation between star formation rate and radial luminosity to select everything that has a radio axis compared to what you expect for star-forming galaxies as an AGN, for example. So in the cosmos field, luckily, we have a wealth of multi-wavelength data. So there's over 30 bands of deep observations, which allow us to have very precise photometric redshifts for our sources, but also the multi-wavelength observations allow us to have a go at various approaches to select AGN. So given that all of our catalogs are public and we wanted to produce also a public catalog with the most flexibility for everyone to select their own sample as they find is needed for their own work, we selected sources in various ways. So in total, we first correlated our radio sources, of course, with the optical and near infrared catalogs, which led us down to about 7,000, close to 8,000 sources with excellent photo-Zs. So first of all, we then selected X-ray AGN, mid-infrared AGN, and AGN selected via the fitting of the spectral energy distribution in galaxies into a category that we call moderate to high radiative luminosity AGN. And then we relied on rest frame optical colors to select red from blue galaxies, which we then sorted into star-forming galaxies. So those are blue and green galaxies and red galaxies if Herschel selected, and low to moderate radiative luminosity AGN, which are the red galaxies. Now there is an overlap here, and this is because we have an independent criterion, which we call radio axis, which is, I will show this later in more detail, but this is essentially the excess of radio emission a galaxy shows compared to what you expect from its star formation rate. So to summarize this, the cosmos field has a lot of multi-wavelength observations with highly accurate spectroscopic, both spectroscopic, but for a smaller sample, but highly accurate photometric redshifts, which allowed us to classify our sources in various ways using the multi-wavelength data. And now with this, we could finally go on and derive the luminosity functions and their evolution, and then from the luminosity functions go on into assessing the radio mode feedback from the radio perspective. So first of all, we took the radio axis AGN sample. And here is the description in a little bit more detail. So this is radioluminosity over star formation rate, where the star formation rate has independently been calculated from the SED fitting and taken from the infrared as a function of redshift. So the points are all of our galaxies in our sample. The blue points with the error bars are the average of our sample. And the red line is the 3 sigma excess compared to the median here. So everything above the 3 sigma excess is characterized as a radio excess AGN, meaning that relative to the star formation rate in the galaxy, there is an excess of AGN. There is an excess of radio emission, and knowing that the radio emission can arise either from star formation processes or AGN-related processes, this radio excess must be due to AGN-related processes. Hence, these are the radio excess AGN. And taking them and constructing the luminosity functions, we get this result. So the black points here are our results for the radio excess sample in terms of luminosity functions, from a low redshift, 0.1 to 0.4, to our highest redshift, 3.5 to 5.5. And here we compare also our results to various other results that are existent. Those are all the points shown in different colors in the plot. So we find agreement in the lower redshift bins where the bigger surveys with optical spectroscopic classifications, classified AGNs, which is always reassuring that our field, our method, our data is okay. And for the first time, we were able to push the luminosity function to these high redshifts on a large sample. So we modeled the evolution using a simple model, which allows for luminosity density and, which allows for luminosity evolution and density evolution as a function of redshift. So once we have the luminosity functions and the model fit to the luminosity functions, to get to anything that we could relate to the semi-analytical models, we have to convert the luminosity that we were doing our calculations on, the monochromatic luminosity, which was 1.4 gigahertz in our case, to a kinetic luminosity. And this is essentially the rate at which AGN transfer energy to their environments. Because this is essentially the total kinetic energy that the radio AGN contain transfer to the environment. That is the parameter to be compared with the radio mode curves in the cosmological models. And this is very difficult. So by all means, this is the least accurate, most uncertain step in the calculation. And here are the results from the literature, how to convert the monochromatic 1.4 gigahertz luminosity to the kinetic luminosity. And in literature, there's essentially two approaches. One of them is to look at radio galaxies in galaxy clusters. An example is shown here. So the contours are the radio emission. The blue to yellow scale is the X-ray emission. So you see cavities in the X-rays filled by radio data. So from a combination of X-ray data and radio data, you can calculate the power needed to inflate the observed cavity. And these are the points shown here. And one of these lines is a fit through the points. I forget which one it is. One of these lines. You can pick your favorite. I may have not even shown it here. The Cavagnolo has to be one of those, the red one. And the other approach is from minimum energy arguments. So calculating the minimum energy stored in the lobes to produce the observed synchrotron luminosity. And this has been done by Willott et al. In 1999. And they have taken carefully all the uncertainty in this calculation into account and conveniently put them in one parameter they call FW, and the uncertainty is 1 to 20. So it's quite a lot. So the Willott et al. Relation is shown by the black line here, and it is within the range, and the slope is approximately there when you compare it to all of the other lines, which are more or less based on the upper method. And here in this particular case, the black line is shown for the FW equals 15 parameter. So hereafter, we're taking the Villot et al. Conversation to see what we get in terms of the kinetic power density as a function of redshift, which is what we show here. And our results from the luminosity functions I have shown you are the blue and the red lines. For the Villot FW equals 4 correlation. And these dashed lines are the limits of the other possible FW FW possibilities, 1 to 20. So what we compare it here to is the green line. And this is one of the curves that I have shown in the very beginning from the Croton et al. SAGE model. In terms of the power versus redshift. So there is some agreement, which may be encouraging, but I would definitely take it with some caution, in the sense that there is a lot of simplifications in the cosmological models and also a lot of uncertainties in the observational step. So we continued to explore this in various ways. And one of the next steps we have taken is to look actually if we have missed any AGN-related emission from this part of the diagram, which is dominated by star-forming galaxies. But certainly composites can be within this diagram, because even if the emission is dominated by star formation processes, there certainly can be emission from AGN also within these sources. And this has been tackled by one of my students, Lana Cerai. She has taken the full sample of our sources, so without any distinctions between star-forming and AGN galaxies. And she has taken a statistical approach to calculate the fraction of AGN emission within the source's total radio emission relative to the expected star formation rate in the source. And we can do this with the Cosmos data because we have independent star formation rate estimates. So in essence, the assumption is the total observed radio luminosity is a combination of star formation related luminosity and AGN related luminosity. From the infrared luminosity, which we have for our sources, we can calculate the star formation rate. From the star formation rate, using the infrared radio correlation, we can calculate the radio emission we expect from star formation related processes. And then going back up here, knowing then the star formation related processes and the total radio luminosity, we get the luminosity of the AGN within a source. And when this is done on the full sample, where we show here the Q parameter, which is the infrared over radio luminosity parameter as a function of redshift, you would expect star-forming galaxies here. And in the color scale, the AGN fraction is shown. So the AGN fraction is as expected 0 in the star formation galaxy region, and it decreases as the excess of radio emission increases. However, compared to the radio excess AGN, where we simply put a cut somewhere here and took the sources with obvious excess, we are now able to statistically calculate within each source the fraction of the AGN-related radio luminosity. These are the resulting luminosity functions. It's a bit of a complicated plot. Low redshift is here, our highest redshift is here. The blue line in every panel shows the total luminosity function of our sources, and you see the bump here, which is due to the star-forming galaxies. And the black dots that you see in each diagram are the luminosity functions calculated taking this fraction into account. So these are essentially the AGN luminosity functions, then the black dots, which we then modeled using the same simple model, converted in the same way to the kinetic luminosity density. And here is the result. So our results are the dots. Our model is the gray model. And this is shown for the conversion with the VLA-FW factor of 15. Again, the SAGE model is shown here by the black dot. And now we're above it because we use FW in this representation of 15. Previously, we used FW of 4. What is added to this is also the Gall-form model. So the total feedback curve from that model is shown by the dashed black line. And in this particular model, they distinguish AGN feedback in two parts that they call starburst mode and hot halo mode. So the starburst mode is essentially consistent with thin disk accretion, and the accretion there is assumed to be due to disk instabilities and to mergers. But it is related to radio emission of the sources. So the radio emission is calculated also in this type of feedback. And the hot halo mode is something similar to what is in the SAGE model. So it is the hot halo feeding the supermassive black hole and causing the radio outflow in that way. So it's a mess, I would say. The two models themselves are offset, and our results reproduce some of the features of one or the latter model. But again, there's very many simplifications in every single approach that goes into this plot. So there's a lot of more work to be done to understand this more carefully. And the last results that I would like to point out is something that my current student is working on, Bruno Schlaus, and let me just note, he's looking for a postdoc. So the approach that he has taken is a wedding cake approach. So here is a luminosity versus redshift plot for various surveys. And so far I have focused the results on the COSMOS survey. So the COSMOS survey is fantastic because it's a deep survey of a 2² degree in the sky. So it allows you to go high in redshift. However, you're missing the rarest objects because to select the rarest objects, you basically need a survey that is wide in area. So the best approach is essentially to combine various surveys in a wedding cake approach, where you take deep surveys of a smaller area and grade them up to the largest surveys, which are not that deep, but they cover a wide area. And this is what is shown here. So the COSMOS survey is combined with the XXL South and North surveys, which together cover about 50 square degrees of area. And this is combined with surveys such as the third revised Cambridge catalog, which have been studied already in terms of luminosity function evolution by Willott et al. 2001. And here are the results of the luminosity functions. And what I would first like to point out that in the Willott 2001 study, using only the brightest, widest area surveys, what has been found is that there is a bump in the luminosity function. So these are the dash dotted results shown here from Willott et al. So Willott et al. Have modeled the luminosity function, separating them into two populations, which they assume to be the low excitation and the high excitation radio AGN. And by modeling their sample, they have shown that the high excitation radio AGN, which are at higher luminosity, evolves more strongly and different than the low excitation radio AGN. which in essence leads to this bump in the luminosity function that becomes more visible at higher redshifts. So with all the data in hand now, we wanted to test whether through different approach, we see the same thing. And we went on to study the evolution of the luminosity function in this combined sample over many decades of radioluminosity. So through a Bayesian approach, Bruno applied many models, but the best fit model in the end turns out to be the luminosity dependent density evolution model. And our results are shown by the reddish area in the background. So similarly to Willett et al., we do find that at higher redshifts, there is a change in the luminosity function due to the higher luminosity sources. And again, doing what we have done before, here are the results that can be compared with the Galform and the SAGE models. And now our results are shown by the gray curve. And what is to be noted here is that now we observe a flattening of our results in this area, so at a redshift beyond 2 or so, that we haven't observed before. For comparison, there's again the SAGE model, as in the previous plot. The full Galform model is the black curve, and the Galform model divided into their 2 modes, the starburst, thin disk accretion mode blue, and the red is the hot halo mode. So we observe this flattening at higher redshifts, and it turns out that this flattening actually arises from the brighter sources that are now in this combined sample taken into account and that have not been taken into account previously in the smaller surveys. And this is obvious from the luminosity density versus redshift divided into various luminosity bins. Therefore, the lowest luminosity, so you see that the peak is somewhere below 1, but as you add the higher luminosity sources, which are constrained in the higher luminosity surveys, the bigger area surveys, you get contribution that starts dominating at the higher redshifts. This is still under construction and investigation. So to conclude, I would say that the kinetic luminosity exerted by radio AGN may possibly be high enough to balance radiative cooling since a high redshift, but there is absolutely no complete agreement between either the models themselves or the observational data compared to the models. So instead of answers, I think we have more questions here to be resolved. And from an observational point of view, the next steps would be to tackle, of course, the conversion between the kinetic luminosity to, between the observed luminosity to kinetic luminosity and its dependence on, for example, environment and other properties, but also to look at sources in more detail to see on source per source basis whether AGN feedback as assumed in cosmological models is plausible, given also there some examples have been found of actually positive AGN feedback rather than negative AGN feedback as assumed in the models. So thank you very much. I will finish with the summary.
Thank you so much, Vernesa, for your very nice talk and covering a lot of grounds. And very impressed by the deep VLA survey. Wow.
Thank you.
I'm sure there are questions in the audience, and I'll pass the...
Yes, thank you for a nice overview. I have a generic question. It was known in the past that between radio loud and radio quiet AGNs or quasars, the radio quiet were the dominant population with 90% versus 10%. But as you said, it depends on the sensitivity of the surveys. So what is the situation now? It seems from the number you showed in the Cosmos, I saw a small number, 1800 versus 1600 or something like that.
So when you look at quasars, as they would be selected in the Cosmos field, we actually find less than 10%. And it's not clear why this is happening. So we're roughly at 4% of the sources being quasars as you would define quasars. So it's unclear why we find less than 10%. It might be the size of the field, but we're not sure.
Any other question? Let's see.
Yes, thank you for the nice talk. You compare, no, you don't compare. You take into account the contribution to the radio emission, both from the star formation in the galaxies and from the AGN. But those two things may vary on very different time scales. Star formation in galaxies in general doesn't vary, well, in time scales of hundreds of millions or billions of years. In AGNs, the accretion efficiency or the amount of gas to be accreted can vary on much shorter time scales. So how do you take into account, because I know nothing in this field, but even modelers, how do they take into account this variability of the AGN?
You mean variability in the observed data or the time scales for star formation and AGN activity?
Vary a lot. I mean, even in small galaxies which are bursting, the time scale is of hundreds of millions of years, not much smaller. But in a black hole, the time scale is much, much smaller for variation. So how is this taken?
So from an observational perspective, it's not explicitly taken into account. From an observational perspective, we use the star formation rate that we compute based on SED fitting or infrared data to select out the part associated with star formation rate processes. So the remainder must be AGN. And in that approach, we don't have to explicitly take into account any sort of variability. In terms of models, the ones that I have presented, it's, I think, not taken into account. It's very, very simplistically approached. As far as I understand the models, but I'm not an expert in the models.
This could explain some of the difference. I mean, for instance, what would you do for a black hole than the one in the Milky Way? We know it's there, it's 4 million solar masses, but it's very inefficient.
It wouldn't be,
and
right.
People think that it's a native accretion. So
yes.
Such kind of black holes, how do you take them into account?
We wouldn't detect it probably in our sample unless it had detectable radio emission to enter our sample. We would not detect it at all. So it would probably lie within the optical sample, not selected in our AGN sample, in our radio AGN sample, nor in the X-ray AGN samples, nor in the infrared AGN samples. So it would essentially be lost.
Hi, Simona Mai from APC. You said you're not an expert in models, but you already gave an idea what are the possible bias from an observational point of view for flux conversion and luminosity conversion. Do you have an idea from your observational intuition or thinking? Do you have an idea what is missing in the models that you would suggest to add to better explain what you are observing?
Taking into account the radial luminosity in a more physical way would be my first thing. And this is what I think Galform has approached in a much better way than the models I have known previously. And in the Galform model, they do actually use the Blandford-Znayak mechanism to compute in a more physical way the radial luminosity that they would observe. However, again, So in the thin disk models, they have a scaling relation where they just scale the radial luminosity a little bit arbitrarily to a lower luminosity. So from that perspective, I would like to see a more physical approach to actually computing the radial luminosity that they would observe from the accretions that they get in their models.
So Jane?
Thanks for the nice talk. So I'm interested in the spatial distribution of these radio AGNs in relation to the last item, the number 4. So on average, the radio AGN could balance radiative cooling. But does it mean that there is enough radio AGN every corner of the universe so that every single space of the universe can be heated by radio mode, or you have very bright radio AGN in some very sparse, some localized regions, and just the region around them can get enough heating.
So it's a function of stellar mass. When you look at the radio sources in when you look at massive galaxies in active radio mode, it turns out that at least at redshifts below about 1, you get to essentially 100% of massive galaxies being radial out. And when you take into account their position in groups or clusters, most commonly the central galaxies are radio bright. So in that sense, for massive galaxies, there would be enough potentially heating by radio jets. And for the brighter sources, I think it's still a little bit unclear how they contribute. So what we're seeing from our data is at higher redshifts, the higher luminosity sources start contributing more than the lower radio luminosity sources. So it's still to be investigated, the answer to your question in that context.
I don't know if there's any question online. There's none. Okay, perhaps I have the last question here is, if you look into the future, I was wondering what future facilities like the SKA will bring in that topic. You thought about this, or?
I have. I think we need better models actually to make sense of the physics in the background. I don't think that at this moment I would go in the approach of a new facility that would bring us better observational data. I think the observational data is already good. Resolution would be better to resolve depth and resolution, essentially to resolve the radio sources better and to overcome any possible out-resolution problems that we may have in surveys like the VLA-COSMOS would be one point to make. But I think we could reach that at least for a subsample with the facilities that we already have. What I would love to see is a more physical approach to modeling and maybe even more of the not statistical aspects like I have presented, but source by source aspects where you can really in detail investigate whether the radio jet is actually inducing star formation rate or terminating star formation rate, and source by source studies for many sources that, again, you can get something more statistical to say on average they are increasing star formation or decreasing star formation. But I think we can reach much of this with current facilities, actually.
That's interesting. Thank you. I think there's no more questions. So let us thank again Vernesa for that wonderful talk.
Thank you. Thank you.
Thank you.